Okay, hey everybody. Today in office hours, we got a couple questions, a couple people asking some questions. There wasn't a video from Tuesday because nobody came to office hours on Tuesday, which is fine. You don't have questions, don't come to office hours. But it's also a good idea just to set time to study. So moving on to questions. We're going to look at mastery question set 4, problems 1 and 3. And we're going to look at the crystal structures activity 10, 11, 12, and the idea of coordination number. I'm going to start with just talking about coordination number and kind of the idea of the crystal structure in general. So in general, the whole point of this is we spent the last 2 weeks kind of talking about individual atoms. And we're at this point where we're starting to build up, well, what happens if I have 2 atoms and they're next to each other? What happens if I have lots of atoms next to each other? And we're starting to build up these structures, particularly for solids, ionic solids, metallic solids. We start to get these regular, repeatable patterns. And we're trying to figure out why this happens, what kind of physical properties it gives rise to, and what kind of interesting chemical properties we can get out of it. To look at most of this, we're going to go to the crystal structure simulator. Just because I'm not good at drawing. So here we are looking at body-centered cubic, right? So this is one of the possible patterns. We've got a couple, there are a lot of interesting patterns that come up, but the 3 that we see most often are the simple cubic, the body-centered cubic, and the face-centered cubic. The face-centered cubic is kind of one of the most difficult to see what's going on. You'll notice the face-centered cubic, just looking at the differences, getting away from all of the other abilities we want to develop while we're looking at these, you'll notice that these 3, just in terms of the way they look, have different packing densities. So if we were just thinking about physical materials, structures that have the face-centered cubic geometry, you'll notice the body-centered has some empty space inside of it, and the simple cubic has even more space inside of it. So there's going to be this difference in density between the materials, which is pretty interesting, right? So we can start to think about how this is going to give rise to physical properties. The problem is, we don't really want to just look at, this is what, 4, 16 times 4, 40, 50, 52 or something. There's like 50 plus atoms here, but when we think about physical materials, we want to think about hundreds of thousands of millions of trillions of atoms. And that's where we get to the idea of unit cells. What we're looking at here is essentially the atomic picture, and the unit cell picture, if we take this and we split it up, the unit cell would be like this piece right here, right? It's one cube that's a nice repeatable pattern. And there's 2 main properties we want to look at. There's the number of atoms in the unit cell, and then there's the nearest neighbors to each atom in the unit cell. And the number of nearest neighbors is the coordination number. And that was one of the things that people in office hours were asking about. So if we looked at these, we have to keep track of the fact that there's a difference between atoms at the edges and atoms in the middle. And the difference we're looking at is really a fictional kind of difference. Really, if we wanted to represent a physical material, we would see this structure expanded a trillion, billion, zillion times. Takes too long to draw that, takes too much computer power to do that. So we're just looking at a little bit of it. But we, in our mind, need to kind of imagine that there's another layer of atoms around this, and then another, and then another, and then another. So just an infinite, almost effectively infinite progression of atoms. This is the reason I like this assignment, and the reason I like thinking about this is because, I'll be honest, most of you are probably not going to use crystal structures much in your academic future, in your careers. But what you will definitely use is 2D representation of 3D objects. How do I take something that exists in the 3D world and make a representation that other people can understand? And how do I understand other people's representation? So this assignment is really a practice of 2D to 3D representation with this kind of bend towards chemistry. So if I wanted to look at the coordination number of one of these atoms, I'd really want to pick like this one in the middle. I'd pick that guy that I'm pointing at right there. And I would say, how many atoms are closest to it? How many atoms are touching it? And that number of nearest neighbors is the coordination number. It's kind of hard to see. I actually think it's easier to see on this face, where I can see clearly there's one above, one below, one to the right, one to the left, that are all the same distance away from each other. This one that's diagonal is further away, so it's not a nearest neighbor, so it doesn't contribute to the coordination number. But this one above, below, to the right, and to the left, those are all same distance away, as is the one behind it. And if we extend this in 3 dimensions in our mind, so is the one in front of it. So we are going to end up with a coordination number for this atom here of 1, 2, 3, 4. Behind is 5. And then the one in front that's not drawn is 6. So we end up with a coordination number of 6 for that one. And actually, if we go to any of these in simple cubic, we'll end up with a coordination number for 6 in all of them. It's a little bit more difficult to see that in the unit cell picture, because if we're looking at this in terms of the unit cell, I can see it's touching on the corners for 4 of them, but then I have to extra use my imagination to imagine what it looks like when all of these are crunched down on top of each other. So it's harder to see coordination number in the unit cells. It's much easier to see it in the atomic picture. We'll look at another one, body-centered cubic. This one, the coloration between the grays and the reds is really just there to make it easier to see the layers and to make it easier to see the difference in positions. But if you look at it, this should really be like a pure compound. And if we look at it, if I look at this gray atom here, it's got the 4 reds below it, all touching. It's not touching any of the gray atoms. It's only going to be touching the red ones. So it's got the 4 below it, and it's going to have another, if we expand this picture in 3 dimensions, it's going to have 4 more touching above it. Or equivalently, if we could imagine getting all the way inside there and considering that one right in the middle, it would end up with 4 reds above it, 4 reds below it, coordination number of 8. Equally, in this case, if I looked at this red atom in the corner, I can see that it's going to have the 4 grays in the face touching it. It's going to have these 4 grays in the next layer behind it touching it. So it's also going to have a coordination number of 8. Coordination number is the nearest neighbors. And even when I say touching, it's electron clouds bumping into each other. Touching gets weird when you're on the atomic scale. But it's the nearest neighbors. Does that help clear that up to some degree? Was it Sophie?
Yeah, that clears it up a lot. Does that mean like for every single body-centered cubic, it will always have a coordination number of 8?
Yes, for pure compounds. And this is going to be something important as we go on to the crystal structures activity 10, 11, 12. The 3 structures we've looked at, simple cubic, coordination numbers always 6. Body-centered cubic, coordination numbers always 8. Face-centered cubic is really hard to see, but yeah, if we have a face-centered cubic, we're always going to end up with the same coordination number. And if we look at this gray one here, you can see it's touching 4 in the same layer as it, a red, 2 grays, and a blue. It's It's also going to be touching 4 in the layer behind it, 2 reds and 2 grays. And if we extended this into 3 dimensions, it would be touching 4 in front of it as well, 2 blues and 2 grays. So in face-centered cubic, we always end up with a coordination number of 12. Face-centered cubic is by far the hardest to see the coordination number. Body-centered, I think, is the easiest. Simple cubic's not that bad, but face-centered, it's really difficult to see the coordination number. But for these pure compounds, we always end up with the same coordination number. When we go to our mixed compounds, like sodium chloride, here the color difference is actually communicating different elements. Or if we go to calcium fluoride, here the color difference is actually communicating different elements. And so we actually do end up with a difference in coordination number because we have different elements present. So we have to be careful about whether we're talking about pure compounds or ionic compounds. So are we ready to talk about some ionic compounds?
Yeah, that was the question I think I put in the chat.
Yeah, so this is looking at crystal structures activity problems 10, 11, 12. So this is a step further. And I will also say Dr. Campbell just had me post a set of slides to go along with this activity that walks through the questions a little bit and kind of gives more of the definition. So if you like the PowerPoint slides, there's some PowerPoint slides for this as well. When we're looking at these mixed compounds, one of the important things for this is this legend button over here. This is where it tells us what the different things are. So the white spheres are calcium, the kind of mustard orange spheres are fluoride, the purple spheres are sodium, and you can't see it very well there, but the green spheres are chloride. So when we go back to sodium chloride, this structure, what we're looking at here, is sodium ions and chlorine ions in some repeatable pattern. And we want to figure out how we look at this. Now we want this repeatable pattern to extend in 3-dimensional space 1 trillion more times. And so to make that easier to do, instead of looking at this and thinking about it in terms of atoms for each thing, we're going to look at a unit cell. And this unit cell, if we just repeat this simple piece 1 trillion times, will build out the entire crystal structure of sodium chloride, which is the salt that we think of when we think of salt. We have to be careful because in chemistry, salt is a broad category of many things, whereas in most of the world, salt just means sodium chloride for people. In chemistry, salt means something different. But when we're looking at this, so looking at this sodium chloride. Now, since we're dealing with a mixed compound, we have to count the sodium ions separate from the chlorine ions. They're 2 different things in this unit cell, which is why we have question 10 is determine the number of sodium ions, and question number 11 is determine the number of chlorine ions, because we've got 2 different things in the unit cell. For me, I find the purple, the sodium's easier to do. So if we look at this, and we just try to just look at the purple spheres in the unit cell, can you tell what structure just the purples make? It's one of the cubics. Hopefully you're all just shouting it with mute on. So if you're watching the video or if you're at home, just yell it to your cat or your dog or your parents. They'll have no idea what you're talking about, but that's okay. If we see this, these purples, they have the simple cubic picture, but they also have 1 on each face. So it turns out that the purples are face-centered cubic. So there's 2 ways to go about getting the number of purple atoms. One is we could just remember face-centered cubic has 4. And then if we recognize face-centered cubic, we're like, great, it's 4. If we don't remember that, we have to remember the kind of cutting idea, which is to say, put this back together. If I have an atom at a corner, I'm going to essentially cut it. Let's see, can I? Oh, that brought that up. Oh, that's not what I want to do. Are you seeing that line I'm drawing?
Yeah.
Interesting. Okay. So we're going to essentially cut this once, twice, and then 3 times back along the other way. And if you take something like an apple, and you cut it once, that's going to give you a half. You cut that half again, you're going to get a quarter. You cut the quarter again, you get an eighth. Now, can I erase the annotation? There it is. Erase. Okay, thank goodness. So the purple atoms at the corners are going to be eighths. And we're going to end up with 1, 2, 3, 4, 5, 6, 7, 8 corners. So we're going to have 8 corners at an eighth each. On the face, we only cut it once, so we end up with halves, and we've got 6 faces. So that's going to give us 1 plus 3. That's going to give us 4 purples. Again, the trick here is the way we represent things versus the way that they actually exist. So how does it exist versus how do we look at it? This is an easy way to look at it, but then we have to have this kind of extra thinking for how it actually exists. The green atoms are a little bit harder to see, because if you look at the green atoms and you shout to the room with mute on, or however you want to shout, what pattern it looks like, you might not be shouting anything, because this doesn't look like any of the other patterns we've had. That's because it's an offset pattern, but that's okay. We can still use the same idea of having fractions of atoms in order to figure out what's going on here. If the corner was cut 3 times, it's got 1, 2, 3 faces. That's how we can tell it was cut 3 times. On the edge here, it was only cut twice, so we're going to go to a half to a quarter. So these edge pieces, these 4 edges here, are 4 quarters. And then we've got another layer of 4 quarters. And then we've got our back layer of 4 quarters. So that's 1, 2, 3. And then we also, whoop, too far. Hiding right there in the middle, we've got another one. So we end up with 4 green atoms as well. Now, why does this make sense? Does anyone, you can put it in the chat or you can unmute and say it. Do you know what the charge on sodium is from our periodic trends? Okay. Let's take a look at something on the periodic table. I'm going to stop sharing my screen for a minute. So if we take a look at the periodic table, there's a couple repeatable things that we can look at on the periodic table. One of them is things in the first column, which we call the alkali metals. Those things typically have a +1 charge to them. Things in the second column, the alkaline earth metals, those typically have a +2 charge. We can make sense of that from our crystal structure understanding, our electron configuration understanding. If we looked at lithium, sodium, potassium, rubidium, those things all have 1 electron in their valence shell, so if they lose that 1 electron, they get to their closed shell, they're going to have that +1 charge. Same thing is true for the opposite side. if we looked at things like fluorine, chlorine, bromine, iodine, those just need one more electron to get to their closed shell, to get to something that looks like a noble gas. So those form -1 charges. So when we look at sodium chloride, I don't have purple, so I'm going to write it in black. And then for the Cl, we ended up with 1, 2, 3, 4, 5, 6, 1, 2, 4, 8, 12 at 1/4 plus 1 equal to 4 Cl. So looking at our crystal structure, we counted 4 sodiums, we counted 4 chlorines. And what this tells us is the ratio of sodium to chlorine is going to be a 1-to-1 ratio. Right? We're not going to write it as 4-to-4. We're going to want the smallest ratio possible. So I'm going to do, since they're both 4s, I can just make that a 1-to-1 ratio. And I'm just going to write NaCl. So this is how we get from counts in the unit cell to the empirical formula. And we can also use the empirical formula to help us figure out what we should get for our counts in the unit cell. So I think that's 10, 11, and 12. So when we're talking empirical formula, we're talking about the smallest possible ratio of cations to anions. I see a couple other questions to add to our list to do today. So that was kind of 10, 11, 12, and coordination numbers. I see crystal structures number 4, mastery questions number 1, 3, and we'll add 6 to that list. Let's keep going with crystal structures for now, and then we'll go back to the mastery questions. So let me see what question 4 is.
The last problem.
Pardon? Yeah, go ahead.
Last problem. What would you use the charges of NaCl? Like, what would those tell us?
Ah, okay. So there's a couple things. So how does the charge come in? So right now, this was on 10, 11, and 12, looking at the number of atoms. We could also look at 13 and 14, which is looking at coordination numbers. Coordination number has to do with charge. So if we think of this as having a plus charge, and this as having a minus charge, it would make sense that the pluses and minuses attract to each other. And every positive one would attract a negative one. So if we had a plus and a minus, then there's a balanced attraction there. If we had something else, like if we had, I'm just going to make up, I'm going to pick something else. If we had magnesium bromide, since magnesium has a +2 charge and bromine has a -1 charge, we would actually see this has a different ratio. It wouldn't be a 1-to-1 ratio. It would be like a 1-to-2 ratio. And it would have a different crystal structure than we'd see for sodium chloride. So that's how charge can kind of get us to this idea of expected ratios as another way to think about this. Most of the time, what we do is we actually, in experimental senses, we go from the X-ray crystallography, using X-rays to kind of get the crystal structures, to get those kind of computer simulation pictures. And then from those crystal simulation pictures, we can figure out the empirical formulas. At this level of chemistry, we could really do it either way. Okay. Let's take a look at number 4. So number 4, okay, unit cell. Okay, so number 4 is asking about what kind of atoms we see in each of the different unit cells. Simple cubic, face-centered cubic, body-centered cubic. So let's go ahead, let's switch back to looking at our simulator. And most people that are having trouble with this are having trouble because of syntax and just what we type in. But if we look at simple cubic, and we're just going to look at one unit cell, you'll notice it only has corners. right? There's nothing on the faces, there's nothing in the center. So for that one, we're just going to say corners. For the body-centered cubic, corners and center.
Can you share your screen?
Oh, I'm so sorry. I forgot to share my screen. It's in the recording, but not shared with all of you. Wait, I just shared the wrong thing. Hold on. Okay, there we go. So, simple cubic. We only have it at the corners. Nothing in the middle, nothing in the faces, nothing in the edges, right? Only corners. The center of each atom is at a corner. So we'd only write corners. If we go to body-centered cubic, we have the corners again. That's the similarity between the body-centered and the simple cubic. But we also, shockingly, have one in the center of the body. Thus the dramatically creative name body-centered cubic. So this one we have to do it in the right orders. So this would be corner, comma, center. And then for the face-centered cubic, we've got the corners again. The coloration is to help us see the layers. We've got the corners again, so another similarity to simple cubic. But now we've got faces with, it's hard to see because of the size of the atoms, but there's nothing in the middle there. You can see right through to the other side. If I zoom in, you can see there's no atom there. This is all four kind of pressing in. So the dramatically creative name face-centered cubic has the corners and the face. Interesting side note, face-centered cubic is probably the most common structure we see in nature. When you look at this, this is if you had a crate of oranges and you put them together, they would kind of stack on each other this way, kind of filling in the spaces between each other and having this kind of higher density. When you got a crate of oranges, they don't balance on top of each other like this, like we see in simple cubic. The reason we have that happen in simple cubic is because our materials are not perfectly round objects, right? We spent last week learning that the electron clouds around these atoms have shape to them. And so they're not perfectly spheres because they're not all just s orbitals. And the shape to them makes it so we get these different packing structures as possibilities. Did that clear up question 4?
Yes, thank you.
Great. If we're looking at mastery question 1, what we're looking at here is how we draw the electron configurations. Again, because of the way LabPal works with letters, these are very syntax specific. That is to say, you need to make sure you get it in the way that it's trying to look for it. Particularly, if I remember correctly, we really wanted to look at the last one, xenon. The main way I like to do this is using the periodic table. Dr. Neff's video on how to do electron configurations goes through the diagonal method, but at the end of it goes through how we use the periodic table to get electron configurations. And I think that's the best way to do it, unless you're going to be going to photon emission spectroscopy and doing it a completely different way. But let's go ahead and look at this. So we can essentially, I'm going to mark this up a little bit. Well, that might have been overkill. There's the S block. These aren't designed for paper. That's okay. The periodic table. So if you've ever heard the term infographics, that's just graphics that convey a lot of information. The periodic table, in my opinion, is the most fantastic infographic. The amount of information hidden inside the periodic table is just incredible. So if you've ever wondered why you've got this like narrow 2 column and then this kind of like broader 6 column and then this kind of wide 10 column in the middle, that's because of quantum mechanics. That's because of the subshells, the S subshell, the P subshell, and the D subshell. And the S subshell has space for 2 electrons, so it ends up being 2 wide. The P subshell is 6 electrons, so it has 6 wide, and the D subshell is 10 electrons, so it's 10 wide. Then if we wanted to do xenon plus 4, I know I said I was going to do sulfur, but I decided everyone seems to be doing okay with most of these, so let's just jump to the hard one. If we're doing xenon plus 4, there's a lot to write. I'm going to do the horrible thing of writing it all out. So I'm just going to follow along the periodic table. 1s2, and this is for xenon. I always like to do, when I have ions, I always like to do the neutral version first, and then change from the neutral version to figure out what the charge is. So I'm going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 1, 2, 3, 4, oh, 1, 2, 3, 4, 5, 6. Okay, gotta keep going. 5s2, 4d10, 5p6. Double checking. Yes, okay. And the reason I went too far is because there's a shortcut we use. We almost never write out the entire electron configuration like this. What we do is we recognize that this to here is krypton. And so this is called the noble gas shortcut. Anything up to a noble gas, we can just use krypton for that. So if I did that in my head, I would just go krypton, and then I would be able to just do the next row below krypton. And a fine answer for xenon, not xenon plus 4, would be krypton 5s2, 4d10, 5p6. On LabPal, it asks you to not include the brackets, but if you ever write it down, it's a good idea to include the brackets. Now, when we start losing electrons, it gets more interesting. So now let's go ahead and look at xenon plus 4. And by convention, I don't mind whether it's plus 4 or 4 plus, I'll know what you mean. But by convention, we put the charge before the plus. So in this case, I want to lose 4 electrons. Now, the funny part is, the losing order and the filling order are slightly different from each other because it's dictated by energy. And when we're just kind of, the trick we have of reading this off the periodic table is correct, I would say probably about 90% of the time, 95% of the time. There's a few exceptions where the energetic order is different. That's part of why we've got this change in order where I go 4s2, 3d10. That's because of energetic arguments that we're kind of glossing over this quarter. To get into kind of that energetic argument's a lot of extra work. I think it's interesting, but it's a lot of extra work. So when we lose our electrons, we're just going to lose these p electrons first. So we're going to have krypton 5s2, 4d10, 5p2. That would be our electron configuration. Now, what's interesting is right now this is written in filling order. You might also see this in losing order. The losing order is actually slightly different, again, because of these kind of energetic arguments. The 4d after this is full is actually going to be harder to remove electrons from. So sometimes you'll see it written where the thing that's going to lose electrons last goes first, 5s2, 5p2. So in this way, I'm going to lose my p electrons, then my s electrons, then my d electrons. And that just has to do with whenever we have a d orbital, we lose the s electrons before we lose d electrons. We have to be careful. There's a lot of exceptions when you're looking at the d orbitals, and we're not going to get too heavily into those exceptions this quarter. But you can see it written either way. That was master question 1.
I have a question about that.
Sure.
One, actually. When I put that in, I got the rest of them right, and it just says no results found for the one we just did with that answer. Because that's what I tried like before too.
It says no results found.
Yeah, that's what it says. Like when I put anything else in, it says it's wrong, but then when I put the answer in, it says no results found.
That is probably my fault. I went through, so earlier today, it was only accepting this answer, and I went in and I changed the code so it would accept either answer, and I probably have a mistake in the code someplace that I have to go fix.
Okay.
So if you get no results found, you probably did it right.
Okay.
But I'll fix that right after office hours.
Okay, thank
Oops.
you.
Trying to make things better and I broke it. Darn it.
Real quick on that
Sure.
problem, will the idea of what loses electrons first, what section or orbital, will we have to know that type of stuff for the test?
For most of them, yes. I don't think we're going to do anything with losing d electrons, and I'll double check with the other instructors and make sure we don't include that on the quiz. I'll write a note of that as well. We agreed we agreed as a group earlier in the week that we weren't going to do that.
Okay. Just like the ordering of what loses first.
Yeah. I think it's fair for simple cases, like everything through the S's and P blocks, but mixing in the D blocks is something we said we were going to put off to the side. Tabitha, what section are you in?
Let me check. It's 2204. Is that the first one? 12701.
01, that's the part I needed. Okay. Let's see here. I want to see if I can figure out why that's not working. 12701 has had some really interesting problems. We're not entirely sure, and this was master question set 1. We're not entirely sure what's going on, but there was a problem with it. Okay, let's see here. Conditions. Okay. Oh, Wait, no, that should be fine. String check. XEP. XE4P6. XE4P6 1. XE4P6. That's 2. XE4P6. It's 2. 5, 2, 4, 10, 5, 2. So you're putting in 5s2 krypton kr space 5s2 4d10 5p2.
Yeah.
And it's giving a weird result, right?
Yeah, it just says no results found.
Huh. Really weird. Can you share your screen with me real quick? I want to take a look at that.
Yeah, how do I do that?
Oh, I have to give you permission to do that.
If it's like on a different tab, it'll still share?
So, I believe so. Let's see, advanced sharing apps. So you should be able to share your screen now. If you see there's a little button down at the bottom of your Zoom that says share screen. And when you click on it, you'll get a list of different things you can share.
Okay, can you see that?
Yeah. Okay, go ahead. Try refreshing the page and putting the answer in again.
5S2, 4D10, 5P2. Yeah, it says the same thing.
What? Try doing Krypton 4D10, 5S2, 5P2.
Did try that one too.
Does it give you no results as well?
So that's true. Yeah, same thing.
Wow. So it's right. I'll have to play with the code and figure out what I broke.
Okay.
Let me try one more thing. Try refreshing the page and doing it again. I just updated the code again to see if it would make it work again, but no idea. No idea. Do me a favor, delete everything in this cell. Huh. I'll have to mess with that. I don't know what's going on there. Weird. I'll have to mess with it. Sorry. I'll figure that out. But you're doing it right. That's something I'll have to fix. Moving on to other questions. Okay. The other question that was asked was mastery question set 4, problem 3. And that one is actually done in the practice problems. The crystal structure practice activity, that mastery question is actually actually, rather than writing that, hold on. I changed my mind about what I wanted to write halfway through. That one is actually calcium fluoride. So if you're looking at that problem, you can actually open up the crystal structure simulator, and you can play with calcium fluoride to get the right answer. So it's the empirical formula, coordination number for yellow spheres, coordination number for white spheres. Most important things to remember in this problem. First important thing for getting the counts correct is make sure you're cutting your atoms to get the unit cell. Right now it's showing you the picture it gives you is the atomic picture. That's very often when we give these pictures, we give them in the atomic picture, assuming that people can make the necessary cuts to make the unit cell in their minds. So anything on a corner is going to be cut 3 times and give you 8ths. Anything on a face is going to be cut once to give you halves. And anything not on an edge, corner, or face will be a whole atom. Second thing to remember, and this is for coordination number. So that's for empirical formula. For coordination number, you have to remember that it's 3D extension. So that white atom on one of the corners actually has 1, 2, 3, 4, 5, 6 other unit cells around it that we're not picturing at the time. So you have to kind of do that expansion, that 2D, 3D kind of mental mapping activity in order to get those. I don't remember who asked that question, but did you have anything specific you wanted to ask about that?
More just what the coordination number for yellow spheres was, because I like and I can't figure that out.
The coordination number for yellow spheres is pretty difficult to see. Let's go ahead and switch back to the simulator and see if we can see it. Again, using the trick that this is actually calcium fluoride, we might be able to see it a little bit better. So switch to calcium fluoride. Ooh, kind of hard to see. Ooh, that doesn't necessarily make it easier, does it? Let's see here. Trying to get it to rotate to a nice spot, and I broke it a little bit. I think with the screen sharing, it's freaking it out some. There we go. Okay, there we go. That's what I wanted to get. So, when we look at one of these orangish atoms, and I say, okay, well, what's the nearest thing to it? It's hard to tell, but it's actually these white atoms are closer than the orange ones. And that makes some sense because we know that the orange atom is the fluorine, the white atom is the calcium, and so the positive charges should be closest to the negative charges. When I'm just focusing in on one of these, I can see that there are two above it that are touching it, and there are two below it that are touching it. There's nothing in the middle, so it's really just these two above and these two below that are kind of like in this weird diagonal pattern. So that's going to be a coordination number of 4. What we're going to learn about next week, there's a special name for the type of geometry around this, where you've got this kind of like 1 up and then these 3 down. That's going to be a tetrahedral geometry. So it's going to have, that coordination number of the fluorines in this unit cell is probably one of the hardest things to see. Do you see how I'm kind of like rotating around and trying to get a good look at it?
Yeah.
And that's really what it kind of takes. And the idea is someday you practice enough that you can do that with your mind.
Thank you.
I didn't want to give them the answer, Jared. I wanted to make them think about it. There is also, if you click on coordination number, it gives you an easier way to look at it. So you can see that kind of mental, if I could rotate it the right way here. It's trying to give you a kind of an easier picture. You can see the 2 up, 2 below. And this is actually going to look very similar to what we're going to see as methane next week. So that was question 3. Oh, question 6. Okay. So question 6 is something different from this unit cell stuff. Give me just a minute to scroll down to that. So, looking at math through question 4, problem 6, this one is a bit interesting. It's got, I'll go ahead and read the problem to you. Which electron will have the highest value for Z effective? The outermost electron in chlorine, chlorine minus, argon, potassium, or potassium plus? Don't just guess. Draw pictures and figure it out before typing your answer. Note the answer is case sensitive and should be typed exactly as shown here. Now, what we've got here is one of the problems with LabPow that is, it's exploitable, right? Since there are 1, 2, 3, 4, 5 choices, and we allow an unlimited number of guesses, you just try all 5, you get your point. But you're missing the understanding that's necessary behind it. And as you know on the quizzes, you get 1 try. So we want to make sure we can get this on our first attempt. So how do we think about this? there's a really fantastic video on Z effective. I think it's optional this week, but I strongly recommend that you watch it. It goes through a great explanation of Z effective, how we can think about it, and how that gives some deeper understanding of the periodic trends. But essentially what we want to think about for each of these is the nucleus versus the outermost electron. And we want to know how many electrons are here blocking between the nucleus and the outermost electron. Z effective, by definition, is how, so Z is the number of protons in the nucleus, and in an ideal world, the electron out here would perfectly see the nucleus minus 1 for each electron that's there. In reality, the electrons that are here are also going to push that electron away a little bit, so you get some modification to how well that electron is being pulled towards the nucleus, which is where you get the effective nuclear charge, Z effective. So to think about this, we want to look at chlorine, chlorine minus, argon, potassium, and potassium plus. And for each of these in our thinking, there's kind of a couple main things that go into Z effective. Typically, if we think about this in kind of the simplest sense, Coulomb force, more protons means more attraction, means more Z effective. More electrons, if we've got the same number of electrons and we increase the protons, we're going to see Z effective change. If we have more electrons without changing the number of protons, you're going to have more electron-electron repulsion. You're going to see a decrease in your Z effective. So these are not like one then the other. It's like one consideration and another consideration. So let's go ahead. Again, I'm going to grab my periodic table, and I'm going to look at chlorine. So I'm going to look at chlorine, chlorine minus, argon, potassium, potassium plus. And what I want to look at in each of these is I want to look at the number of protons, I want to look at the number of electrons, and then there's actually another thing we should also consider for Z effective. It's not perfectly true, which is why I didn't include it before, but more shells, meaning further distance away from the nucleus, that's also going to have an influence on Z effective, and typically more shells means less Z effective. It's a little more complicated than that, which is why I didn't include it in my original two. So chlorine has 17 protons, 17 protons. Argon has 18 protons. Potassium has 19 protons, 19 protons. So as we go up, potassium's got more and more protons. So this should be potassium plus, more protons. But we're also, as we go up, we're increasing the number of electrons and we're increasing our shells. So we've got this kind of competing of two ideas. Let's go ahead and look at number of electrons and see how that compares. For number of electrons, 17, 18, 18, 19, 18. The thing that I noticed right away when I was looking at this problem was I've got 18 electrons, 18 electrons, 18 electrons. Now this is, after we have this thinking, this is where the more shells is where we can start doing that kind of like pictorial thinking, which is where it says, try drawing pictures. So when we start thinking about this, I'm going to start with thinking about chlorine 17. I'm going to have 17 protons in the nucleus, and I'm going to have my 1s. I'm going to just change colors for this. I'm going to have my 2s, my 2p. Now these are not all perfectly spheres. This is just a representation. I'll just switch back to this 3s. And then this is the 3p, which is where we're going to have chlorine. And we're going to have 1, 2, 3, 4, 5, 6. So the 7th electron that's going to come in, notice these 6 electrons all have the same kind of equal pushing of core electrons. Right? This whole mess in here makes the core electrons. And they're going to have that equal pushing. But adding another electron without adding more protons, that's going to be less Z effective. So chlorine 17, chlorine 18 is out. Chlorine 17 versus argon. So if I increase the number of protons in the middle, 18 protons with those electrons, same number of shell, but more attractive, I think that gives argon a slight lead over chlorine. Now, the difference between potassium and potassium plus. If we go to potassium, sure, we get another proton, but we're also going to be adding an extra shell that's going to be a much larger shell. So that's going to create a problem. That's not going to be as good. But if we go to potassium plus, where we've got more protons than electrons, that's the dead giveaway that it's going to have a nice Z effective. So more protons than electrons with a full shell, I think potassium plus is going to be the right answer. I think. I'm going to put it in and see what I get. I'm not going to tell you what I got. You've got to do it on your own. But that's the kind of thinking that we go through. Again, there's a really nice video that I think walks through it better than what I just did. And they've got these nice graphics and images that do it as well. So I would say check that out. That was the last question of that. I see we've got another. Let's take a look at lead 4+. Any questions on this before I move on? Okay.
So having more rings makes the Z effective greater.
Actually, having more rings makes the Z. Well, it's a balancing act, right? It's how many rings versus how many protons versus how many electrons. Usually having more orbitals, right? They're not typically rings. That was a kind of a cartoon picture because I can't actually draw orbitals that well. But typically having more shells decreases Z effective. The reason that potassium was the winner was because you have that extra shell, but when you go to potassium plus, you lose that extra shell. So potassium by itself is probably the worst Z effective. But potassium plus is probably the best Z effective because you lose that shell.
Okay, cool. That makes sense.
Okay. So, going back to mastery question. Mastery question 4, problem 1. Looking at lead 4+. Now, I'm going to not do it the long way I did the last one. I'm going to just jump straight to the shortcut. There's lead. So I'm going to look at it. It's going to be xenon. That's going to take care of the 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Oh, no, that takes care of all of that up to the 5p6. Isn't that a nice shortcut? Love it. And that's going to get us to 1, 2, 3, 4, 5. I'm just counting down the different rows. So I'm going to be at the 6s2. Now you'll notice on the periodic table, hopefully you're looking at your copy. I don't know how that shows up on the screen. But right there's like the lanthanum with a star. And you'll notice that matches up with the star here next to cerium. That's because if we actually drew the periodic table, I didn't draw it very well, but the F block would actually fit in there and we'd get this kind of long, funny picture. So we have to include there, where that star is, where lanthanum is, we have to include the lanthanide series, the 4F14, and then we can come back to the 5D10, and the 1, 2, and the 6P2. This is the fill order off of the periodic table. The loss order, again, is slightly different because we have to take into account the energetics of the electrons interacting with each other after they're there. So the fill order and the loss order are slightly different. When we look at losing electrons, we're definitely going to lose, essentially we lose the highest n values first. So we're going to lose the 6s, we're going to lose the 6p and the 6s first. The order, what I have here, this is just for lead. If we wanted to look at lead 4+, if I did 2+, I'd lose those two. If I did 4+, I'd lose those two. So I would have xenon 4F14, 5D10. On LabPal, it does not ask you to include the empty orbitals. Some people, to accentuate the fact that you lost electrons, will include a 6s0, 6p0. That gives you the idea that there was something that was lost. Most people, especially when you get to higher levels of chemistry, don't include that. We just include the places where the electrons are, not where the electrons are missing.
Okay, thank you.
You bet.
Real quick though, so S loses electrons before D?
It does.
Okay, cool.
Yeah, that's one of the important exceptions in terms of the energetics. We're not likely to ask you questions about that on the quiz, but I think it's really neat.
And the diagram that Dr. Neff showed in her video, is that what that's showing?
It's showing the fill order.
Okay.
Yeah.
Okay, cool.
And it's a weird kind of quirk that the fill order and the loss order are different. And we can get to explanations of why that loss order is different. If we start looking at the radius information for the different orbitals, it turns out that the size of the 6s orbital, even though it's a different energy, the sizes of these orbitals are different. And also, when you start putting in the electrons, we like to draw these pictures like the orbitals are static. But as we put electrons in, they all actually kind of wiggle around a little bit. And it's a matter of where they are energetically relative to each other at their current point. So, not to get too nuanced in this, because it does get very nuanced. Even when you go from lead to lead 2+, all of your orbitals energies will shift a little bit just from losing 2 electrons. Not enough to change the losing order, but we'll see little shifts. In order to actually get those little shifts, you actually have to do a full quantum mechanical calculation of the energy interactions of the electrons with the nucleus. It's really neat stuff, but totally beyond the scope of this class.
Cool.
Okay.
And is there any other place besides the star at LA that continues to the bottom? Maybe the caret?
Yes, the caret does the same thing. Both those rows step in. And we probably won't ask things that far down on the periodic table. Most things at that point on the periodic table are unstable. They radioactively decay. Okay, another fun thing. Theoretically, there's a G block that hasn't been discovered yet.
Wow.
Yeah. as we keep finding new elements and keep trying to determine new materials, theoretically we'll eventually get to a G block. That'll make the periodic table look even more silly.
That's crazy.
Yeah. We're not even close to it. We need like another 25 or 30 elements before we'll see it. But we're getting there.
Oh, I noticed on Dr. Neff's periodic table, like the upper section is like filled on the bottom right.
Yeah. So it depends on the age of the periodic table. I actually have a periodic table app on my phone. Of course I do, right? And they have out to 118 at this point.
Wow.
So they have quite a few new elements. And element 118 was just discovered in 2006.
Wow, that's crazy.
So, brand new element. It's got a little bit of history. Was not actually completely confirmed until 2015.
Wow, that's very recent.
Yeah, so that is the reason I like having the app is it's got all kinds of fun history about the elements. It's got the electron configurations, common oxidation states, but it also updates. So as new things get figured out, like it's just like, oh yeah, update.
That's cool.
So, yeah. I'm gonna go ahead and